The top left box shows the valence shell electrons in a molecule of beryllium hydride, BeH2. Notice that beryllium has 2 electrons in its valence shell and forms 2 covalent bonds with hydrogen atoms. The bottom left box represents the shape of a beryllium hydride molecule. Click Labels to label a covalent bond and the bond angle. The large box on the right shows a diagram of the molecular orbitals in beryllium hydride. The bonding pair electron repel each other. The orbitals are pushed as far apart as they can get, sticking out at opposite ends of the molecule. You might describe the shape as linear. Move your cursor over the diagram to rotate the structure. Select Ball and Stick from the menu. Notice its stick-like appearance. Move your cursor over the diagram to rotate the structure. The top left box shows the outer shell electrons in a molecule of boron trifluoride, BF3. Notice the bonding and non-bonding pairs of electrons in the outer shells of the boron and fluorine atoms. The boron atom has 3 covalent bonds with fluorine atoms and no lone pairs. Click Labels to see a covalent bond and the bond angle labeled. The bottom left box shows a ball and stick diagram of this molecule. Why can't the angle between the bonds be less than 120 degrees? Answer: this would bring 2 of the molecular orbitals closer to each other. The large box on the right shows the 3 molecular orbitals of a boron trifluoride molecule. Move your cursor over the diagram to rotate the structure. Now select Ball and Stick. Move your cursor over the diagram to rotate the structure. The molecule can be described as trigonal planar. What does this tell you about the shape of the molecule? Answer: the 3 covalent bonds are all in one plane. Boron trifluoride and ammonia have similar formulae, BF3 and NH3. But they do not have similar shapes. Ammonia has trigonal pyramid shape. Why? Answer: boron trifluoride does not have a non-bonding pair of electrons, while ammonia does. The top left box shows the valence shell electrons in a molecule of phosphorus pentachloride, PCl5. The central phosphorus atom has 5 covalent bonds with chlorine atoms. Click Labels to label covalent bonds and bond angles. The bottom left box shows bond angles for a phosphorus pentachloride molecule. Some are 90 degrees and others are 120 degrees. How many angles of each size are there? Answer: 3 of 120 degrees and 6 of 90 degrees. The large box on the right shows an orbital diagram of phosphorus pentachloride. Mutual repulsion of the 5 bonding pair electrons pushes the orbitals as far apart as possible. Move your cursor over the diagram to rotate the structure. Select 3D Model from the drop-down menu. The large box on the right shows the 3-dimensional arrangement of chlorine atoms around the central phosphorus atom. Move your cursor over the shape to rotate the structure. This structure is a trigonal bipyramid. How many faces does this structure have? Answer: 6. Select Ball and Stick from the drop-down menu. Move your cursor over the diagram to rotate the structure. Not all of the angles between covalent bonds in a phosphorus pentachloride molecule are the same. Why? Answer: for the molecular orbitals to get as far apart as possible, a trigonal bipyramid structure is formed. This has 2 different angles. The top left box shows bonding and non-bonding electrons in the valence shells of atoms in a sulfur hexafluoride molecule, SF6. Notice that there are 6 covalent bonds between the central sulfur atom and fluorine atoms. The bottom left box shows a ball and stick diagram of this molecule. Click Labels to label the covalent bonds and bond angles. The diagram in the large box on the right shows 6 molecular orbitals arranged around the sulfur atom. Move your cursor over the diagram to rotate the structure. Select 3D Model from the drop-down menu. The large box on the right shows that the atoms in this molecule of sulfur hexafluoride, SF6, are arranged in an octahedron. Move your cursor over the diagram to rotate the structure. How many sides has an octahedron? Answer: 8. Select Ball and Stick from the drop-down menu. Move your cursor over the diagram to rotate the structure. Each covalent bond is at an angle of 90 degrees from the 4 covalent bonds nearest to it. Why are all of the bond angles the same in a molecule of sulfur hexafluoride, but there are 2 different angles in a molecule of phosphorus pentachloride? Answer: for 8 molecular orbitals to get as far apart as possible, the structure must be an octahedron, which has equal angles between all of the bonds. The table gives a summary of the molecular shapes we have looked at. What is the effect of non-bonding or lone pair electrons on the structure of molecules? Answer: the presence of lone pair electrons results in the distortion of regular shapes such as a tetrahedron, so the bond angles are less than in the undistorted shape. Summary. Valence shell electron pair repulsion theory predicts a number of different shapes for molecules. In each shape, the bonding pair electrons occupy a position as far away from each other as possible. Molecules may be linear, planar, tetrahedral, pyramidal, V-shaped, bipyramidal, or octahedral, depending on the number of lone pairs and bonding pairs of electron. Different molecular shapes have different bond angles. The diagram in the top left box shows the arrangement of valence shell electrons in an ammonium ion, NH4+. Compared with an ammonia molecule, the ammonium ion has a fourth hydrogen atom, but no extra electrons. The additional hydrogen atom is joined to the nitrogen atom by a dative, coordinate, covalent bond. The bottom left box shows the shape of an ammonium ion. Click Labels to see covalent and dative covalent bonds labeled in the top left box and the bond angle labeled in the bottom left box. The large box on the right shows the molecular orbital arrangement for the ammonium ion. There are 4 identical molecular orbitals, each with the same amount of repulsion from their negative charge. This results in a tetrahedral structure. Move your cursor over the diagram to rotate the structure. This tetrahedral structure for an ammonium ion is similar to that of methane. From the menu, select 3D Model to see this tetrahedral arrangement. Move your cursor over the diagram to rotate the structure. Now, select Ball and Stick from the menu to see a ball and stick diagram of an ammonium ion. Again, move your cursor over the diagram to rotate the structure. Note that the angle between any 2 covalent bonds is 109.5 degrees. Why is the bond angle in an ammonium ion different to that in an ammonia molecule? Answer: the ammonium ion has 4 bonding pairs of electrons, whereas the ammonia molecule has 3 bonding pairs of electrons and 1 lone pair of electrons. Consequently, in the ion, the tetrahedral shape is not distorted. The top diagram shows the arrangement of electrons in the valence shells of atoms in a hydroxonium ion, H3O+. Click the Labels box to label bonds in the top left box and bond angle in the bottom left box. Why does this structure have a positive 1 charge? Answer: the oxygen atom provided both electrons for the dative covalent bond. The ion is therefore 1 electron short. The diagram in the large box shows the electron orbitals of a hydroxonium ion. The non-bonding pair of electrons occupy an orbital that exerts a greater repulsion than the 3 molecular orbitals. As a result, the shape is trigonal pyramid. The angles between the covalent bonds are less than the tetrahedral angle of 109.5 degrees. Move your cursor over the diagram to rotate the structure. Why is the bond angle less than 109.5 degrees? Answer: the lone pair electrons has a greater power of repulsion than the bonding pair electrons. This pushed the molecular orbitals closer than the tetrahedral angle. From the menu, select 3D Model to see a diagram showing the three-dimensional arrangement in a hydroxonium ion. Move your cursor over the diagram to rotate the structure. Select Ball and Stick from the menu to see a ball and stick model of this ion. Move your cursor over the diagram to rotate the structure. The shape of a hydroxonium ion is similar to that of ammonia. Summary: valence shell electron pair repulsion rules can be applied to predict and explain the shape of polyatomic ions.